Welcome to the Metabolic Classroom. I am Professor Ben Bikman, a biomedical scientist and professor of cell biology. Thanks for joining me. In the episode or the lesson this week, we are discussing the hormone leptin. Leptin enjoys a lofty position within the realms of endocrinology and in just public interest. It's one of those hormones that, because it deals with metabolism and fat tissue, it's become very popular. And for good reason. As we go through this lesson, you're going to really appreciate not only some of the aspects that you are already familiar with, and we will discuss those, cover them, and provide some nuance, but also I really want to make a point of highlighting some of what people don't often think of when they think of leptin. To get started, let's just define the hormone leptin and identify where it comes from and then talk about its regulation. But of course, the end goal, once you get familiar with leptin, is to discuss leptin resistance, which is a concept that's become very popular. And it is very relevant, so popular for a good reason. Leptin is it's a peptide hormone, first of all. So it falls in, there are three general classes of hormones. Classified based on its structure. If it's a little string of amino acids, it's a peptide hormone, and that is the vast majority of hormones in the body. Leptin is one of those. The primary source of leptin production is fat tissue. Now, you've heard me joke before that when I teach classes in endocrinology, I make a point of teasing the students with the fact that every organ, every tissue is now an endocrine organ. In other words, everything produces hormones. It doesn't matter what tissue you're talking about. Bone produces hormones. Muscle produces hormones. Fat produces a lot of hormones. Leptin is one of the more famous ones. So leptin is primarily sourced from fat tissue, white fat tissue, but there are some other sources that produce leptin, most especially the placenta. During pregnancy, the placenta provides a great degree of leptin production. So too does muscle a little bit, and even the stomach is capable of producing some leptin. Now, one point that is relevant that we get to later as we start to wrap leptin into the topic of obesity is that leptin levels will track with fat levels. So the more fat a person has, regardless of how, whether it's more abundant fat cells or whether it is bigger fat cells, because those are not the same thing. Someone could be fat because they have more fat cells, even though the fat cells are a little smaller, or someone could be fatter because they have fewer fat cells, but they're much, much bigger. Regardless, as body fat goes up, leptin goes up as well. And that's important to remember. So someone who is overweight or obese, so someone with higher body fat, they are just generally going to have higher levels of leptin. You can take that to the bank. It's going to be a pretty reliable fact. Now let's talk about the regulation of leptin. So fat cells are the primary source, but that is not to say that fat cells are constantly streaming out the leptin, that it's a constant leaking of leptin into the blood just because we have more fat. Not at all. There's some regulation. Leptin, like all hormones, is it's one of the instruments within an orchestra. And there are various directions, there are various cues that are given to leptin to let it know when it's leptin's time to come to go up or go down. All right, so let's transition into that next part of this lesson, the regulation of leptin. And first of all, let's talk about the factors that stimulate leptin secretion, because there are various both physiological and biochemical factors. And here are some of the key stimulators of leptin based on some literature. And of course, as usual, all of these publications, the most relevant ones of what I'm teaching, will be in the show notes. So firstly, you know me well enough by now to know that it's hard for me to talk about any hormone without invoking my favorite, namely insulin. Insulin significantly stimulates leptin secretion and production from fat tissue in particular. In fact, insulin increases leptin by almost double. So it will, whatever the leptin state is, when insulin comes up, it's going to signal to the fat cells to almost double the amount of leptin that is in the blood. And this is primarily coming, in fact, it does so very quickly, quicker than the fat cell would be making leptin from scratch, which suggests that fat cells will have a given amount of leptin pre-created, already created, on hand, if you will. It's ready to go. It's packed up in boxes, ready to be shipped out. It doesn't need to create it from scratch, although, of course, it can do that. So leptin is a very important stimulator, or is most importantly stimulated by insulin. So of all of the stimulating factors that we're going through now, I'm starting with the one that matters most, namely insulin. So let me say that again because I stumbled a bit. Insulin is the primary stimulator of leptin. Another stimulator of leptin is a hormone, which is sometimes referred to both accurately as a hormone and as a cytokine. Now, you've heard me say the term cytokine before. A cytokine is essentially a hormone that regulates immune function or inflammation. One of the most famous and relevant to this conversation is TNF alpha. TNF alpha induces leptin secretion, both from fat cells in a little culture or from fat tissue in vivo, or from a living organism. And TNF alpha acts directly on adipocytes or fat cells to stimulate leptin secretion. Interestingly, with regards to TNF alpha, we have here a somewhat uncommon scenario where you have what is called autocrine signaling. An autocrine signal is when one cell will release a hormone, and then that hormone will act on the very cell that just made it, signaling to that cell to then do something else. So in this case, let's bring all those pieces together. We have a fat cell, which, as a fat cell is getting bigger and bigger, as it's getting more and more hypertrophic, you've heard me discuss previously that as a fat cell is undergoing hypertrophy, it becomes ever more pro-inflammatory. One of the reasons is because of everything I just said, which is TNF alpha. As the fat cell's getting bigger, it's releasing more and more TNF alpha. Now, interestingly, as TNF alpha is circulating through the body, increasing this kind of basal inflammatory tone, so making the body a little more inflamed, what is often referred to as a subclinical chronic inflammation. Subclinical just means that it's not like the patient is coming in with evidence of like severe infectious inflammatory signs, like a septic shock or something. So the inflammation is dialed up a bit, but it's not to the point that it's making the person clinically suffer in any obvious way. So we call it subclinical chronic inflammation. So again, we have the ever fatter fat cell releasing ever more TNF alpha, which is then signaling back onto the very fat cell that just made it, potentially, or any neighboring fat cells. That would be called a paracrine signaling. But autocrine, meaning self-stimulating, it releases the TNF alpha. The TNF alpha acts on the very fat cell that just made it, the TNF alpha, to then start releasing more leptin. So inflammation in this kind of chronic subclinical sense, not in like an angry, swollen, infected wound, inflammation is capable of increasing leptin. And then another one, the third and final one that I want to discuss, there are some additional little inputs, but they're very modest. So for the sake of time, we won't cover them. The third and final is unique to women, and that is the effect of steroid hormones. Now, earlier I had mentioned that there are three classes of hormones if we classify them based on structure. One of them was peptide. One of them is steroid. Now, anytime you hear steroid, you should just think of cholesterol, because cholesterol is the base structure. So the tissue or the cell that's making this hormone, the steroid hormone of interest in the moment, and I'll identify which steroid hormones are relevant here, but the cell will take a cholesterol molecule and start manipulating it to create this, what's called a steroid nucleus. That's basically just saying a scaffolding that is based on cholesterol. Then the cell will take that cholesterol molecule and start altering it a little bit, creating any one of the number of steroid hormones. And there are many steroid hormones, not nearly as many as there are peptide, but there are a lot. And in fact, these two are very well known to you. But again, this is unique to women. It's an effect. There might be a modest effect in men, but it pales in comparison to the effect that we see in women. That is estradiol and cortisol. Now, estradiol might be a hormone that doesn't ring a bell. It might not sound familiar. Often, estradiol is referred to as estrogen in a singular sense. However, that's not accurate, and I want to be very precise here because I want to teach you very accurate information. Estradiol is the primary estrogen. And if we're using the word estrogen, we should actually be saying estrogens. The term estrogens is more accurate because it's actually a little family of the prototypical female sex hormones. Now, males have estrogens as well, just not as much, and it's less relevant, although not irrelevant. But within the family of estrogens, estradiol is the primary estrogen. So anytime you hear estrogen, you could actually just think estradiol. So estradiol has a stimulating effect at inducing the fat cells to create and release more leptin. But so too does cortisol. So any given amount of cortisol in a woman will elicit a greater secretion of leptin. Now, I know generally within the realm of social media, a lot of people like to talk about the evils of cortisol in women, and this is why women shouldn't fast or whatever. I've talked about this previously and really attempted to kind of blow that idea up. There is extraordinarily little evidence to support that. In fact, I'm only aware of one single study although I admit this is a tangent, that shows that cortisol levels in a woman will go higher than what you'd see in a man with adoption of a low-carb diet. And however, it was temporary. It happened at about week 2 and then went away. So I really believe that the idea that fasting or a low-carb diet is a unique stress on women, that is not a valid idea. And I think people are hyping it a bit unnecessarily. All right. Nevertheless, that wraps up this little subtopic, namely, again, to remind you, what are the variables that stimulate leptin production? They were, I would submit in order of importance, insulin, then TNF alpha, that pro-inflammatory cytokine hormone, and then some steroid hormones, unique or particularly relevant in women. Now, that talks about what turns leptin on, but what does leptin do? Now let's transition as we discuss further the regulation of leptin. Let's now, within that topic still, talk about the actions of leptin. First of all, leptin's most famous effect falls in this idea of regulating energy balance or just metabolism. And the most famous effect being the suppression of appetite. Leptin will act on the hypothalamus, which is a distinct small section within the center of the brain. And by doing so, by acting on the hypothalamus, it activates satiety centers or signals. Thus, if leptin is elevated in the bloodstream and leptin is working well, then it will tell the brain, it will enhance this sense of satiety. And ideally, then the person begins to eat a little less. Now, that is leptin's most famous effect, but you've heard me invoke similar language with regards to insulin and glucose control, that controlling glucose is insulin's most famous effect, but that shouldn't imply that, in this case, back to leptin, that it is the most important, because leptin does a lot of other things. But just as we're going to get into now, but just still sticking within the realm of energy and metabolism, leptin promotes mitochondrial biogenesis. So it is stimulating the production of new mitochondria, particularly in mitochondria-rich tissues like muscle cells. When leptin comes to a muscle cell, one of its effects, and there are several even at the muscle, will be to stimulate the production of new mitochondria. Now, another central effect, let's transition out of metabolism and just highlight some of leptin's other effects, just so that you can appreciate how important it is. And then with that appreciation, we can appreciate why things can start to go so wrong when leptin isn't working well. Because remember, one of the points of this lesson is to discuss leptin resistance, which we're getting to, I promise. Another effect is back to the brain, which is leptin's influence on the reproductive axis. It should be a very well-known fact, although it isn't. Even still, it's something I've discussed previously. Leptin modulates something called gonadotropin-releasing hormone, GnRH. And that then influences luteinizing hormone, LH, and follicle-stimulating hormone, FSH. Both LH and FSH are important in men too, but as the name suggests, luteinizing hormone, which is reflective of the corpus luteum, a remnant structure when the ovary has ovulated, but also follicle stimulating hormone, with the follicle itself, which is maturing into the egg, which will ovulate. The names of these hormones are reflective of the fertility processes in women. But again, that's not to say they're not relevant in men. They are. Even still, leptin is an essential signal at stimulating GnRH. Let me just really put a fine point in this. If there is, in other words, no leptin in a body, there's no fertility. Leptin is utterly critical. It is completely essential to normal fertility. This is, of course, particularly a problem in women. Women, in part, probably. Now, allow me to speculate a little bit. This is an opportunity where, when I'm discussing these kinds of things with students, I say we have to step out of science and kind of enter the realm of philosophy or speculation, because a scientist can only really ever answer the question of what or how. A scientist can't answer the question why. Why is it that this fat-derived hormone, leptin, is so essential to signaling to the brain that it's okay for fertility to occur? And why is that then so much more important in women? Why is it that the female body is so much more sensitive to leptin, or in other words, requires more leptin in order for fertility to occur than what you would see in her male counterpart? So now we're entering the why. And like I alluded to a moment ago, I like to joke with my students that why questions are divine questions. In other words, God only knows why the system was set up the way it is. Why is leptin so essential for this process? Now we can speculate, though, and that's fun to do. It could be that as women bear the metabolic burden of fertility, it's very important for her body to ensure that it has enough energy to not only provide or account for this substantially increased metabolic rate that's occurring in her body as she's growing this new little human, not only the energy going to the new little human, but the energy growing to grow her own body. Pregnancy is one of the really kind of two instances of substantial growth in the life of a human, the other one being puberty. So her body is growing in a lot of ways in order to help the environment be suitable for the little human to grow as well. So her metabolic rate is going to go up a lot. Having sufficient fat tissue is basically this metabolic insurance. It's the brain's way of saying, hey, how are we doing with regards to our energy reserves? Do we have enough energy on hand to really commit to this? Do we really want to do this, body? Because this is a marathon. Are we ready to commit to this? Fat cells, if there's enough fat cells, there will be enough leptin, and then the leptin will signal to the brain that fertility is okay to go. Now, however, if a woman in particular gets too lean, which too lean to her would be still sufficiently lean for a male to function properly with leptin and fertility. But again, her body needs more fat. And so there is a higher threshold for the leptin in order for her fertility to occur. But as the female gets too lean, getting into the lower mid single digits, she's gone below that threshold. Now there's not enough fat to produce enough leptin to enable the brain to approve fertility. So anyway, I've spent too much time on that, but it's just such a fascinating topic that I can't help but want to discuss it in a little more detail. So leptin, in addition to its regulation of metabolism, which we discussed with appetite and mitochondrial biogenesis, and there's a little more that I'll get to in a moment, but it's essential to fertility. Also, with regards to this kind of neuroendocrine aspect, it also influences TSH coming from the brain. TSH is thyroid stimulating hormone. So as leptin is influencing TSH, if there's too high or too little leptin, it's going to influence TSH, which will then, thyroid stimulating hormone, affect the thyroid and the production of thyroid hormone. This next point isn't perhaps surprising in light of the fact that TNF alpha, a poster child of pro-inflammatory cytokines, stimulates leptin. Leptin also influences the inflammatory or immune responses. So it influences immune function. It, in turn, can then influence the production and stimulate the production of other cytokines that are relevant to immunity. Now, as much as I have been discussing inflammation in a purely negative sense, please keep in mind that it is an utterly essential system, that if we didn't have inflammation, there would be no recovery from a wound. Inflammation is necessary for healing. Inflammation, of course, is necessary for defending the host against infection. So in this sense, don't think of this as being a negative effect, that leptin can increase the production of cytokines, both pro and anti-inflammatory. They're both essential in a normal immune and healing response. One very overlooked effect of leptin, as we go to the next one, is vascular function. Leptin can influence and stimulate the production of nitric oxide. And nitric oxide is a signal that's created by the endothelium, the lining of a blood vessel. And when leptin is sensed by the blood vessel, it will activate the production of nitric oxide, which induces a dilation, vasodilation, or just dilation of the vessel. And that's beneficial for heart disease risk in general, because if the blood vessels are generally a little more dilated, that will lower blood pressure. And high blood pressure is one of the leading risk factors of heart disease. And then one last one, very briefly, is that metabolism also influences bone formation and remodeling. So it's a very helpful one. Another reason why it's so important, particularly for young women, to have sufficient body fat, to have sufficient leptin to ensure sufficient healthy bone mass development. All right. Now, one final point, and perhaps the most important for the sake of the rest of this conversation, is how leptin interacts with insulin. Now, I'm going to make two very important points that we're going to revisit in later points as we go through the next part of this classroom lesson. Leptin inhibits insulin secretion. Let me say that again. Leptin inhibits insulin secretion. So normally, if leptin levels are going up, it wants to bring insulin down. It wants to inhibit the beta cell's ability to produce and release insulin. In contrast, so while leptin is trying to turn insulin down, insulin actually has a more favorable relationship with leptin. So, leptin is trying to beat insulin down, but insulin's trying to build leptin up. So insulin stimulates leptin secretion, and then leptin inhibits insulin secretion. So from the perspective of insulin, which is how I see a lot of things, as you know, it ends up being a bit of a negative feedback. It's one way that the body turns insulin off. So again, if insulin's climbing, it wants to stimulate leptin. And then as leptin is climbing, it then in turn wants to turn off insulin. All right, now I'm going to revisit that. So just remember. Now, as we move on to the next part of this lecture, it's actually a bit of a history lesson, which is just so fun. As I was putting together my thoughts for this classroom in this lesson, I debated on whether I should show this part or share this part with you and teach this history lesson, because I'm not a history professor, as you know, and I don't want to be. I like being a cell biologist, but the history of leptin is just so fascinating. All right. Now, the next part of this lesson talks about the history of its discovery and its discovery in the context of obesity. So in 1994, Jeff Friedman's lab at Rockefeller University really explored this and discovered this new hormone that was produced from fat tissue that they found played an essential role in mice. That was the animal model they were looking at, being thin. Now, importantly, these animals, what they found in this massive animal colony, all housed in their perfectly controlled cages, they got all the food and water they want. It's perfectly temperature controlled, and light dark cycles perfectly suitable for the animals. In some part of this colony of animals, some of the animals had just developed this spontaneous mutation, and they were just fantastically fat. In fact, when you get done, or pause this lecture and just look up an animal called an OB mouse or a DB mouse. They're actually just two versions of the same mouse. Whether it is a mutant, whether it's the animal that doesn't make leptin, DB is the type of animal that doesn't make leptin, or it can be an animal that has mutated to not have a leptin receptor. So it's making leptin, but it can't sense it. That's the OB mouse. So you can just do a little Google search really quickly and look up a leptin mutant mouse, and you'll just see they're in fact super cute. They're just so fat that they can barely get around. And so they were fascinated by this random mouse line in their colony that had become ridiculously obese. And they found that by measuring all the hormones available in the blood, that these animals didn't have a hormone that the thin animals had. And that when they extracted that hormone that the thin animals had, but the fat animals didn't, and they injected it into the fat animals, guess what happened? They became lean, and in fact, extremely quickly. And so he said, Dr. Friedman said, okay, well, this is the hormone that controls being thin. And so he named it after the Greek word for thin or lean, which is leptos. He called it leptin. So now we had the hormone leptin, and this was a huge discovery. It really suggested that this was the key to fighting the obesity epidemic, which of course we know is a fight that continues to just be in full force with all these anti-obesity hormones that have become so popular. This is just the latest version of it. But leptin was one of the earlier versions because, again, they could take this protein, this hormone, and inject it into these super obese animals, and they became lean almost immediately, like within just weeks. All that fat tissue was gone. Then, of course, the next step was to move this into human trials, that they took obese humans or lean humans, both, two sets, gave them the injections of leptin. The lean people, of course, had no effect. They were already thin and they stayed thin. The obese people, no effect. They were overweight or obese before they started the clinical trial of getting leptin injected, and they were still obese or overweight when they finished or throughout the entire trial. So it was an utter failure in human trials. Why might that be? It's because the average overweight or obese individual has very high levels of leptin. Now, if a human has a leptin mutation where they aren't making leptin, which is very uncommon, but has occurred. There are known and published case studies of this. And those are usually instances of just fantastic levels of obesity very early in life. So the average individual who's just getting a little chubby and then getting obese later in life, that's not what we're talking about. Those are the people who have normal leptin function. And in fact, indeed, they have too much leptin because they have too much fat cells. And there is too much insulin, as we'll get to more detail in a moment. But if someone is a true leptin mutant or has a mutation in the leptin gene, then of course leptin therapy is remarkably effective. Now, back to the trial as we transition into this final topic, this clinical trial. Why did it fail? Again, it's because the average individual who's overweight or obese, they have plenty of leptin. In fact, more than they need. And so injecting leptin doesn't do any good. That's because now, but why are they? I mean, if leptin is so helpful for controlling obesity, why have they become obese? Why wasn't leptin working? And how can we reconcile the fact that they have so much leptin? Again, to put a fine point on it, an overweight or obese person will have much more leptin than their lean counterparts will. It's because they become leptin resistant. So leptin resistance is when the body is no longer responding effectively to leptin. And importantly, that's the main part of the definition of leptin resistance. And those of you who've listened to me enough already know where I'm going with the next part. There's another component to leptin resistance, which is high levels of leptin, chronically elevated levels of leptin. Does that sound familiar? Because that's the same way I describe insulin resistance. Insulin resistance is this phenomenon where insulin isn't working as well as it used to, and equally essential, blood insulin levels are elevated. That is the same definition that can be applied to leptin resistance. One, that leptin isn't working particularly well, and two, leptin levels are elevated. Again, this is why injecting more leptin into the average overweight or obese individual does nothing. You're just wasting the leptin. It's not going to work. Now, what are the causes? Now, one final point before I get into the causes of leptin resistance. Earlier, I had mentioned that insulin has this strange relationship with leptin, whereas leptin inhibits insulin. Insulin stimulates leptin. So you've heard me before discuss the fact that it is completely impossible for an animal, human included, to get obese unless insulin is elevated. But so far, I've just been describing a scenario where the absence of leptin results in ridiculous and rapid onset and development of obesity. And now you're wondering, okay, so is the absence of leptin sufficient to cause obesity? Is that all we need? Maybe it's not insulin. Maybe Professor Bikman has been leading us astray. I have not been leading you astray, and I'm very glad to teach you the fact that it is still the insulin that is responsible for the direct growth of the fat cell. Insulin is a completely essential signal to the fat cell, telling the fat cell what to do with the energy that is available to it. Leptin does not do that. And importantly, a lot of people want to assign the absence of that leptin. If leptin is gone, the reason the animals become so obese, or a human with a leptin mutation becomes so obese, is simply because they eat a lot, and they do eat a lot. And so they would say, well, it's just purely calories. Not so simple. So just before I mention that, let me just finish the point that I'd kind of distracted myself from earlier, which is, remember, leptin inhibits insulin. And so if you don't have leptin, guess what has happened to insulin levels? In these animals that are leptin mutants, or even in humans, this is documented in both models, animals and humans. If you take away leptin, there is less of a signal to keep insulin dampened. Thus, insulin levels climb by multiples. So insulin has gone up significantly. In fact, Dr. Friedman himself, Gary Taubes, has quoted this in his book, Good Calories, Bad Calories. Dr. Friedman said that insulin goes through the roof. So it goes up by multiples. So even though leptin is influencing myriad processes related to metabolic function, it is still, at the level of the fat cell, the elevated insulin that is directly causing the obesity. Now, this starts to touch on the caloric versus endocrine theory of obesity. And in fact, leptin is a wonderful example, proof positive that the caloric theory is flawed. Now, you know well enough by now, certainly with previous Metabolic Classroom lessons that I've filmed, that calories matter. The energy matters. But equally, if not more important, is hormones that tell the body what to do with that energy. In fact, I would say more important than the number of calories. So in animal studies that take leptin mutant animals and compare them with their normal leptin litter mates, so these are the same general strain of animal, so same type of mouse, to be more accurate in my language, housed in the identical conditions and given the exact same type and amount of food. And that last point is very important. That's what's called pair feeding. So you take normal animals and pair feed them with leptin mutant animals. They're given the exact same number of calories. And guess what happens? The leptin mutant animals become fantastically obese, even though they're eating the exact same number of calories. Now, again, insulin has gone up by multiples, so it is still the insulin that really matters at the level of the fat cell. But leptin, of course, is the one who's driving the tempo here and changing things. But it is still a necessary change through insulin. But even still, keep in mind, please, when people are saying, no, obesity is just purely a matter of calories in, calories out, this is evidence that directly proves that wrong. That, again, as much as I try to be diplomatic and say, no, of course, calories do matter. And of course, in most instances, we're not dealing with people who have a leptin mutation. But even still, they cannot state, with this such an obvious example in mind of these leptin mutant animals, which are leptin deficient animals, they cannot say that hormones don't matter, that it's purely calories. You can literally give them the exact same number of calories and they will still end up much, much fatter. All right, now let's get to nearing the end here. The causes of leptin resistance. One, the most important, is leptin itself. Just like how I say with insulin resistance, the most important cause, or the primary cause of insulin resistance, is hyperinsulinemia. The primary cause of leptin resistance is hyperleptinemia. So too much leptin drives leptin resistance. A good study, it'll be linked in the show notes, by Martin et al. In 2008, really shows that quite well. But remember, if you think about elevated leptin as being the primary driver of leptin resistance, insulin pushes leptin up. And so it begins to be obvious that any diet that is resulting in chronically elevated insulin, driving insulin resistance separately, is also going to be driving up leptin, which then in turn will be driving leptin resistance. So you start to see some overlap here as we discuss insulin and insulin resistance, and then leptin and leptin resistance. And then, just for the sake of time, another cause of leptin resistance is inflammation. So something like C-reactive protein, for example, has been shown to contribute to leptin resistance. C-reactive protein being one of the other famous, and this one even clinically measured, markers of inflammation. So those are some of the primary causes of leptin resistance, and the consequences are myriad. Of course, as leptin isn't working well, a person may have a harder time controlling appetite. So they'll have a compromised satiety signal and just be more inclined to overeat. They will have a decreased energy expenditure because leptin influences energy expenditure. Of course, leptin resistance, if leptin isn't working well, as I discussed earlier, insulin will be higher. There's less of a signal to turn insulin off. So it's no surprise that if a person has leptin resistance, it can directly contribute to hyperinsulinemia and insulin resistance, because, as I've already stated, high insulin causes insulin resistance. But also, if leptin isn't working, blood vessels are going to be more constricted, which can contribute to heart disease. Reproductive function will be compromised. Immune function will be compromised. Bone development will be compromised. So there can be no surprise. All of the things we talked about leptin doing when it works well won't be working well when leptin isn't working well, or won't be occurring well in leptin resistance. So just to now wrap it up, remember that it's not the absence of leptin per se that is contributing to obesity, or it's not the lack of leptin function per se. It's not the leptin resistance that would be contributing to someone's obesity. It would be that leptin, if it's not working well, isn't able to bring down insulin. And thus it would be the hyperinsulinemia that is really at the level of the fat tissue, directly stimulating the fat cells to grow. Now, what can you do about it? Let's end with some good news. If you are overweight or obese, you very likely have leptin resistance, and you want to try to help leptin work in your favor. To do so, you want leptin to come down, and you want the body to become more sensitive to it, just like you want with insulin resistance. So one of the keys, as I've already alluded to, is controlling glycemia. If you can bring blood glucose down, then you can bring insulin down. And as you bring insulin down, you remove one of the stimulating signals of leptin, and thus leptin itself will come down. A study by Kong et al., and that will be linked in the show notes, in 2020, this was a study out of China, and they took overweight women and put them into one of two groups, a kind of normal low-fat diet or a low-carb ketogenic diet. And the low-carb ketogenic diet resulted in a drop of the high levels of leptin by more than twofold. So the relative drop, here was the baseline for both groups. The low-fat diet had a leptin drop this much, if you will, a couple units, and then the leptin was more than double the reduction. Now, that's a good thing. Don't say that, oh, well, leptin's good, we need more of it. No, we actually want less. We just want it to work better. So this is direct evidence that if you can control the glucose levels, which is, of course, most easily controlled by getting a grip on the glucose coming in, the carbohydrate, then that helps the insulin come down. And as insulin comes down, the leptin will as well. But a final study I wanted to share with you is Shapiro et al. In 2011. Look in the show notes, where they looked at this was in animals, a high fructose diet. So that's, of course, a component of a high glycemic index diet. It can lead to leptin resistance. And when they induced leptin resistance, and then only with a high fructose and high fat diet, so high fructose, high fat diet, induced leptin resistance very quickly. If they just removed the fructose, but kept the fat elevated and replaced the fructose just so equal still calories, other carbs in place, if they removed the fructose from the chow that the animals were eating, but still kept everything else at the same, the leptin resistance got better. Leptin levels dropped and the animals became more leptin sensitive. So there could be a fructose specific effect that contributes to leptin resistance. But of course, even then, it could be related to insulin spiking then leptin. All right. So hopefully there's some good news at the end there. Thanks for joining me. I hope that the topic is interesting and that you feel that you are much more informed. It is a topic that people discuss. Now you certainly are capable of contributing to those discussions, I hope, much more capably than you were before. Thanks again for joining me. Until next time, more knowledge, better health.